Go ahead and get started. Just to be respectful of our time and your time, and thank you for joining us today. We are tremendously happy at Translational Health Research Center to be working with Nicole Wagner and Chris and others at Dreamer Ranch and in ag and across the campus on a really interesting topic that I never thought I would have any relationship with, but that I'm finding more and more. It's something that really excites me, not only for the potential of this research to solve real problems, but also for our institution to build new expertise that is maybe the market isn't quite ordered on yet, and we can do it in a way that will have relevance, because our research mission is intended to be applied and have relevance and do things in a way that are scientific, but not in a way that separates the science from the application. And so this to me is a really wonderful avenue for us to explore. So along those lines, I'm really thrilled to host today Dr. Hugh McLaughlin, and I'm going to read a little bit because I want to get it all right. He's an internationally renowned expert in biochar, activated carbon production and characterization. When I first was introduced to his name, of course, I Googled biochar McLaughlin, and a million hits came up, a lot of videos, a lot of papers, a lot of really interesting projects and studies. And so I was like, wow, okay, we got the right person to come and help us think through what do we need to do to be that school that can be a leader in biological research. Dr. McLaughlin holds a PhD in chemical engineering and is a professional engineer with over 4 years experience in process chemistry and engineering, industrial R&D, and scale-up of new technologies. He's taken many concepts from a lab to scale up to the marketplace, and he specializes in particular in adapting proven industrial approaches and practices to the newly emerging areas of renewable energy, carbon, climate, conscious technologies such as biochar. From 2009 to 2013, he served as director of biocarbon research for Alterna Biocarbon, and his research is rapidly developing the field and has resulted in several publications, as well as 3 chapters in the book entitled The Biochar Revolution. So maybe in 20 years, Texas State will be a leader in the biochar revolution based on the research that we do here across several different disciplines, from chemistry to engineering to agriculture to concrete to who knows what. And I'm thrilled to have him here today. So I would like to introduce Dr. McLaughlin.
Thank you. So thanks for the opportunity. I'm excited. One of my flaws is I tend to have one thing on the slide and talk about something different. So we're going to be recording this whole thing, and you'll be able to review it for the things that I either missed or tangented off, et cetera, et cetera. But I'd like to start off by addressing the elephant in the room. They sent me the announcement, and it said Dr. McLaughlin is an internally renowned expert on biochar. Yes, oh, you did. Okay, before you send it to the rest of the world, well, it was too late in this man's world. I was just cut to the quick. So I'm going to try to address my credentials when it comes to biochar. So we have on the right is Raj Pashari, who headed up the IPCC for many years, 2002 to 15. He made a lot of enemies over those years, putting out report after report after report saying, you guys are headed for a cliff, and it's not going to be a pretty landing. I happened to be at a conference up in Norway with him. He blinked. I got up there and had him take a selfie, and it's been immortalized ever since. I promise you that he's not telling anybody about this day when he met me, frankly, because he passed away. So in any event, I then moved on. That's Johannes Lehmann. He's probably the best known name in biochar. He lives close to me in upstate New York. And I am the repeated, undistinguished colleague that shows up in all these pictures. Just for a moment's structure, we're gonna run the first till about an hour. We're gonna have a talk, really an overview of biochar, some of the myths, some of the misconceptions. Then we're gonna take questions and then a break, and then we're gonna come back for another shorter section that is gonna be much more focused on the future of biochar here at Texas State and how you can create programs and what I see some of the needs are, et cetera, et cetera. There may be students that that's really not on their critical path, and I would invite you to discreetly disappear at halftime, but everyone else obviously is welcome. Continuing on this is the Biochar Revolution, one of the earliest books that came out. I did write chapter 6, what is biochar? Chapter 7, biochar helps the soil. Chapter 8, characterizing biochar, attributes, indicators, and at-home tests. And this work is very early work, but it has held up. And I have spent most of my public involvement in biochar working on characterization. Now, characterization is different from standards. Standards and certifications represent, in my mind, a minimum obligation to meet. A characterization is a measurement of a property and is used to quantify how this material exists in a spectrum of materials and how to match it. So I've been very, very focused on this, and I've done a lot of foundational work, and I'm excited that I might be able to pass it on, cut down some learning curves, and get some people going on this. Let's see what else. Okay, so Mongolia 2013. I'm on the right. Guy on the left is Carl Frogner, another person who's done some fantastic work in this space. The guy in the middle is Genghis Khan. This is a huge statue facing China. This is Mongolia, this little tiny country. They put up a statue going, natty, natty, boo-boo. In 1275, we took over your country, gave it to somebody else. And this really sums it up. I've been doing biochar since 2008. It shows. It was a mystery. When I came into this, I was as clueless as a person who's just hearing the word today. It's not a mystery anymore. This, in my mind, this is an eminently understandable material. It is complicated. It is a natural material, and anytime you have the variations of life, everything is a bell curve instead of being, a Dirac delta, a data point. But it lends itself very well to some scientific rigor and building on your knowledge and taking it forward into other disciplines and having them build on it. So it's not, we don't need this quantum accelerator. We don't need Oppenheimer leading the team. We need people that are willing to roll up their sleeves and do what they're taught to do. Biochar. Let's go into this. Is it new? Is it safe? Who invented it? These are relevant questions. Unlike Al Gore, I did not invent biochar. Biochar was invented by Mother Nature 600 million years ago. So it's new if 600 million years is new in your world. And what it comes down to is in that 600 million years ago, here, we finally got the oxygen down or high enough in the atmosphere out of the oceans to get an ozone layer to get rid of the UV that was killing all the life on land, and we could have plants migrate out of the oceans and starting having land-based plants. And Mother Nature has lightning strikes and she burns out forests, and that deposited 1%, very small amount of the carbon inventory in the soil. And it's been there ever since life evolved out of the seas. So we co-evolved with biochar, we being the microbes, not humans, the microbes, life in the soil, life on land, co-evolved with biochar as a component in soil. So we're not putting something new in soil, we're putting something back that in fact has been missing in a lot of soils that we have artificially created from media like sand and loam and things like that. Many people have seen this curve. I'm sure anybody with any climate consciousness has been beat over the head with this a few times. This is the acceleration of CO2 level in our atmosphere as measured at a very isolated place in Hawaii. The sawtooth is because in the summer there is more vegetation in the northern hemisphere than there is in the southern hemisphere. So there's more uptake of CO2 as they leaf out and they grow. So the downslope is summer. And then when all those leaves fall off, then we switch the seasons and we have the uptick. But undeniably that sawtooth is going up. And if we look at the last 600 million years, and we do this with lots of different techniques, but these are cross-disciplinary, and I don't need that we can argue with the general phenomena, but really the important thing is we're here today. There's only been 2 places in the history of the world, the last 600 million years, that we've had a combination of the low average global temperature and the low, that's the only time we've previously seen the levels of CO2 that we started off with going into that curve. And if we drill into about the last 400,000 years, we're starting to see what I think is, you can argue scatter, you can argue correlations, but frankly, there's a trend there that says when we get high CO2 levels, we get higher temperatures. When we lose the CO2, we drop down. So there's an interaction. And I don't bog down on climate temperature. It's up at 1.5 degrees, 1.25 degrees, because the problem really is the phrase climate, climate change, climate warming is so benign. It's like, yeah, we could go within 2 degrees in the winter. I live in the Northeast, there's snow. It's climate chaos. What we're doing is we're pumping energy into our atmosphere. We have 5% more moisture in the atmosphere now because of the very small warming of the ocean since this industrial revolution. That 5% is what's creating these enormous rain events. Because when it does break loose, it drops that 5% plus what it was going to drop before that rise. And that turns into massive amounts of water. And this is where we are today. We are now at 425. And this, frankly, is the reason I'm still hitting it. This is my timeline. I graduated from high school, it was at 325. I got my PhD, it was at 350. I went back to talk to my undergraduate school in 2010, we were at 390. I'm talking to you, we're at 425. We've gone up 100 parts per million in the last 53 years. That means somebody out there who's 20 years old, when they're up here talking 53 years from now, we're going to be at 525 or 550. And that is, frankly, game over. Even MIT can't cook the book so bad that it makes it seem like 550 is going to be viable. So we really have to get on with this. So here's my conclusions from those kind of macro slides. You can debate global warming, climate change, you can drill down on little facts and you can argue all day long. But at the end of the day, the atmospheric levels are going up. And what the hard part is connecting that global direction with discrete events. The Earth has no problem with that. It's been at all sorts of levels. Our original atmosphere back, 6 billion years ago, we were 30% carbon dioxide in the atmosphere and virtually no oxygen. And only through millennia have we reversed it and converted the CO2 into the oxygen that we now breathe. So we got no problem with the rock is going to be fine. What is the problem is whether our quality of life and civilization as we see it is going to do as well. And frankly, to cut to a chase, we're here to talk about biochar. This represents a discrete methodology that is Mother Nature's original way of putting carbon into the soil, and a way that we can adapt to modern practices and take it to our advantage. It's the same, but it's entirely different. What's different? Well, with a forest fire, I get 1% of the carbon, 1 to 2% of the carbon inventory deposited back as unburned char. It's wood that's been changed enough, you'll see how, but it doesn't burn up, but it's not burned to ash. With a properly designed biochar technology, I can get easily 25% to 50% of the carbon atoms that go in the front end as fuel coming out as this stabilized material that's not going back to the sky. And furthermore, I can make that material have value as a material, not just as a carbon dioxide sequestering technique. So we got to do the CO2 removal part, but I can also make materials with value. And that's the homework part. That's where you just got to put your head down and make it happen. So, how hard can that be? I mean, we got biomass. Mother Nature, through some slow depositions, made it into coal in a scant 100 million years. We know how to do it with carbonization pyrolysis in 100 minutes, so that would be less. How much less? Well, I divide 100 million years by 100 minutes and I get something on the order of 500 billion times faster. So you can appreciate that we just can't turn on the coal making thing, because we can't wait 500 billion times longer. I apologize if the math's off. But biocarbon, furthermore, has been bifurcated over time into two materials. The one that dominated was charcoal. Basically, wood was, prior to coal, was the major energy source, and by making it into charcoal, I had a better behaved energy source. Charcoal is distinguished from wood, and it burns without smoke. So if I'm going to have a barbecue or I'm going to have a campfire inside a cave, I can't be burning wood because I'll end up with smoke inside there and I'll have an inhalation problem. It's a fuel, it's a metal reductant. What's that mean? Well, let's see. Bronze Age, Iron Age, Tin Age. This is what you do. You take charcoal and the ore, get them hot enough, they suck the oxygen out and they leave you the molten metal. So it's a reductant in metal, and that's what spawned all those ages. Mother Nature always made biochar. We've come back to it. About 2005 or so, the concept came out. It was actually stumbled on in the 60s, 1960s, by some Dutch scientists, but they never got recognized. In 2006, Lehman jumped on it, started pushing it. He's done a lot of heavy lifting, and biochar is back as an entity discrete from from charcoal. Charcoal's a fuel. If you're going to use it and make it disappear, the CO2 goes back to the sky, it's charcoal. If you're going to make it into something that's going to stay as that material, it's very stable, as we'll see, and we're going to use it as a concrete additive, as a soil amendment, as a pavement, now we've got a permanent use that ties that CO2 up, that carbon up, and we have a different value add. Not only its performance as a material, but the CO2 sequestration benefit. So biochar is full of pithy little statements like, oh, an old solution to a new problem. So yeah, good, we're good to go. So let's take a look at this. I want to drill down into this a little bit. When we convert biomass to either charcoal or biochar, we heat it, we basically transform it into a new material. We break the old bonds, we get rid of parts of it as vapors, and we make this new material. Its amazing property is it's different enough from what it started out as, is the soil microbes no longer can use it as fuel. There's two theories why that is. One is it's too complicated. Make it three theories. It's too complicated for them to have enough enzymes to take it apart because of all the permutations. Two, it's too stable. It turns out that the reason it formed is it dropped into a very low energy state. Graphite, if you happen to be a chemist, represents the most stable form of carbon. If I take your diamond ring and stick it in a hot enough muffle furnace, I will successfully make biochar, which may not make me much of a good husband, but it will at least make my point that graphite is the stable form. That's where it goes. And it doesn't break down. The third one is that the microbes know better than to eat the hardest thing to eat out there. And that's where the graphite comes in. It's just more work for them to turn it into a fuel, to get energy out of it, so they don't. They eat anything else in the soil before they do that, including themselves. So it stays. This line is pretty flat. It's flat for a century, for a millennia. We have charcoal on the walls of caves in France that they just used charcoal from the fire and they drew, and 38,000 years later, exposed to the humidity changes, not direct sunlight, but a lot of weather, it's still there. So this stuff doesn't go away. This stuff is stable. It does go away, and I did this study in the lab, and it's very tedious. It goes away in a million years. So if you put charcoal out, it will in fact slowly degrade with the low level of ozone in the air over a million years. But if we can get a million years down the road, we're going to have a lot of things solved. Versus the uncharred material, which is going to degrade, frankly, in the sort of 5 to 10 to 20 year range. You can walk through a forest with downed trees. There's some remnants there, but that wood has changed enormously. It's rotting. It's going away. So this is what's called the short carbon cycle. And what happens is trees grow. I'm not telling you anything you don't already know. they grow and they make sugars out of sunlight and water through photosynthesis. So they pull the CO2 out of the air, they join it with water they bring up from the ground, they add the energy from the sunlight, and they make these 3 carbon sugars that get made into 6 carbon sugars, and now they have an energy stream. They use half that energy stream being a tree, just running the machinery of that tree. So the rest of it gets to build into tree. It gets used for what are called exudates, so that sends it down in for soil microbiology. It's used to grow the seed, the leaves, all the other good stuff. But at the end of it all, when the tree dies, we then go into this microbial breakdown and we recycle all that CO2 back up to the sky. And it just keeps going in a circle. How do we know this? If 1% didn't break down over time, in 600 million years, we'd have 15 feet of it everywhere. So it becomes so obvious that there was a portion that doesn't break down. Mother Nature recycles everything, given the choice. And if I do some math here, 200 CO2 molecules get pulled out of the sky by the tree as it's growing. It makes 200 carbon atoms of sugars. That's its commerce. It uses 100 of them to metabolize for the energy it needs. It sends 100 of them down into the soil. They then break down. They all go back up. Life goes on. A lot of other things are being recycled in this mode. The nutrients and the plant fertilizers, the phosphorus, potassium, etc., they all drop and break down and get released into the soil. But the carbon end of it is completely going in a loop the whole time. Now here's what we're proposing with biochar. We intercept that portion that was headed at the end of the tree's life. We're going to do something to it, and we'll get into that. And we're going to pyrolyze it. Well, that's going to result in half the carbon atoms of the 100 that went down going into the soil as biochar, and half of them going over into the bioenergy piece, which can be either used to release energy as a fuel source, which sends the CO2 back up, or you can make chemicals and water and other good things out of it. So it's got potential. And I also have a small portion of the biochar that then does degrade because it wasn't fully fixed, and I show that with this carbon release 5% number. So we're being rigorous. We're not sleight of hand. If I do this math, the 200 come in, 50 end up going down into the biochar, 10 go back up as the recycle of the tars, 50 get here, a lot of things. 40 carbon atoms. So the tree in one day uses up 200 carbon atoms from the atmosphere. And through this whole cycle, 40 of them end up in the soil for centuries. That's a 20% yield. I was a consultant for many, many years. That's like saying every dollar of net revenue I get in, I get to put 20 cents into my IRA. I wouldn't be here working. So, that's a phenomenal yield. This isn't 0.1%. This isn't going in circles to try to make small gains. This is a huge engine. Yeah, it's not 80%, but there's reasons it's not 80%. The starting material is only 50% carbon. I can't expect to get all 49 carbon atoms in the soil, but 20%, frankly, is huge. And I get this energy stream, and that's equally as significant. I get 70% of the energy of the entire biomass stream coming in, exiting as a usable stream for chemicals and water, or as an energy stream. And then I capture all these carbon atoms. So it's working for us. Now, it can't compete with natural gas and oil in today's marketing and market economies, but that's fine. Here's a typical breakdown of a wood, and we've thrown some stoichiometry on this so we didn't play sleight of hand, and we see it making into a biocarbon. It's a solid. We call these the inert gases, although water is going to condense. And we've got these pyrolysis tars, and this is the breakdown of the carbon matrix. I've got 57% of the carbon atoms initially. This happens to be a fairly low temperature char, and that's why you see that much in tars. So it's not fully representative because when you do the science, you see it's very much a function of temperature. And really, we start with biomass up to 200 degrees. We're basically just drying it out. And then we start seeing this transformation, and we get the fixed carbon content going up, Residual yield dropping off dramatically. 3/4 of the weight leaves as vapors. 1/4 of it's left behind. But that quarter's got half the carbon atoms. So it's a great partitioning process. It's pretty amazing. And we've got similar trends with carbon and oxygen. The carbon, it's, when we talk about pyrolysis, we talk about carbonization, making a more carbon-rich solid. Pyrolysis, heating stuff. Devolatilization, taking off the volatiles. That's where the oxygen and the hydrogen and a fair portion of the carbon's going. And now we got to ask ourselves why. How'd that happen, Mac? Well, I have an undergraduate degree in chemistry. I have a couple other degrees in chemical engineering. And all we got to do is go from a tree all the way down into the molecular structures of which we end up with the 3 major components in biomass. And with this context of biomass means vegetable matter. It doesn't mean animal matter, because animals tend to be a lot more water and fat, and neither makes good biochars. So plants, on the other hand, tend to be lignocellulosic. So we got cellulose, lignin, hemicellulose. And they are interwoven almost at the molecular level. They are not, however, colored, those colors. I think that's important to point this out, because these are the colors that they really are. It's time that we got honest about this. So this is another depiction. You've got the cellulose. Those are the concrete pillars that make the strength in biomass, the stiffness. And you got the lignin, this hemicellulose tying to it and weaving it around. And then lignin is this waterproofing agent. That's really the key to lignin. Very different molecules, but very, very close together, almost on an atomic. They're pure forms, but then there are also so many adjacent interfaces. And so when I go from the 100 degrees up to 200 degrees, very little happens. But as I go from 200 to 300, I go through stages of this drying. Glass transition is a polymer term. Depolymerization and recondensation. Limited carbonization, extensive. We've dramatically changed this material. Every bond in biochar is a new chemical bond. At least it's in a new combination with other chemical bonds. The volatiles took off. We made these graphene sheets. So as we lose a volatile, all of a sudden I got carbon atoms that are no longer correctly valenced up. They interact and start forming these 6-membered rings. Because of the thermodynamics of it all, they make graphene, graphite. Remember that stable material that I turned your diamond ring into? And that is why these things start forming. And when we get done, we create this 3-dimensional structure of these rigid graphene sheets that are curved, by the way. They're like soccer balls. They have defect. A lot of 6 members, but there's 5s and 7s. And it's massively porous. I mean, it really is. It's 80–90% just volume of air and vapors. And that's one of the properties of biochar. It gives you a rigid structure that can hold moisture or hold air in the soil. So it helps aeration and it helps moisture retention. You should probably sketch this if you're watching this talk. You really want to capture as much detail. So this is activated carbon is a sister material. Biochar is Mother Nature's activated carbon. So there's a lot of properties it shares. It shares the absorption property. It's not as optimized for it. But this is the molecular depiction of activated carbon. And at this level, these dots are atoms. This is so small that you can't even imagine it. You always see these pictures in biochar. We look at the SEMs and we see the little boxes and the pores and all this other stuff. That is the forest, and you want to be looking at the acorns. This is at such a molecular level. It's so incredibly tiny. Has anyone ever been to Legoland in California? Can you explain to me why the bars aren't open at like 6 a.m. at Legoland? Because that's the first thought that occurs to me when I get to Legoland is I need it. So they make structures out of Legos, right? So I'm going to make a 1 millimeter biochar particle. So that's a millimeter, 40,000th of an inch. Every scientists know what a millimeter is. And I'm going to make a 1 millimeter cube on edge out of Legos. But the Legos I'm going to use are potato chips. So I'm going to use a potato chip 2 inches across. and I'm going to pile them up until I get this pile of potato chips that's the equivalent of the 1 millimeter biochar thing. And so the question is, how big is this cube of potato chips that represents the scaled up 1 millimeter biochar product? Any guesses? I've given this talk so many times. One guy goes, the moon. It's bigger than the moon. I go, thank you for being reasonable about this. It turns out that pile of biochar, potato chips, is 4 miles on edge. 4 miles across, 4 miles deep, 4 miles up. That's a lot of potato chips. So that's how far down we have to go in size to start seeing the actual molecular level interactions that biochar brings to bear. It's a material that we could not make unless Mother Nature just gave it to us. It is so much smaller than the smallest computer chips. It's amazing. And you can make it in a million different ways. You can make it for small money. You can make it with a top-down burn with a pile of brush. And that's what decods. So let's tie up some loose ends. And that will wrap up this first section. I want to answer questions on this. So how does wood burn? What's with terra preta? You've heard that. And options for slash piles at Freeman Ranch. You can see the tension just, you know. As you know, we have collected wood at Freeman Ranch for a while. We attribute this to Chris's propensity for wanting to save every branch that comes across his path. But let's start with, how does wood burn? Well, let's bog down in some science here. Wood, it's got these 3 components. We saw that as we heat them up, they all start falling apart at different temperatures. Turns out they fall apart very quickly once they actually get to the temperature locally. But wood is essentially evaporating off, and that cools it. So it's like an ice cube that vaporizes and keeps itself cool. So there's a tremendous heat duty associated with getting wood to vaporize. The lignin, the cellulose splits off at a different temperature. The lignin splits, volatilization cools, and we get this stuff down. We put it all together. What do we got? We got a match. A match does it perfectly. You light it. The flame migrates down. The heat comes back down and heats up the next bit of the match. It vaporizes off, that makes the flame, and the flame migrates down. It exits the other side, it cools off fast enough, and voila, we've got the char. Wood burns in 2 steps. When I heat wood up, it devolatilizes and carbonizes into char, gives off these gases, they can be burned. If I then later have oxygen attacking the char at high temperatures, that does char gasification, and it burns to ash. It's what I call the Boy Scout campfire. If you've ever worked with Boy Scouts, their idea of a campfire is a pile of kindling about this high. Nice thin stuff. You light it, poof, you get these big yellow flames. It's heating up all that wood, devolatilizing that all. Fast forward to the end, I got a pile of red embers. It's all char turning to ash. And in between, I've got a combination of the 2. So I've got this 2 different steps involved. And if I look at a campfire, I can actually see all these steps occurring. I've got wood in that white arrow that hasn't even gotten hot enough to start becoming char. I've got red embers over on the right-hand side. I've got yellow flames, which are volatiles coming off that burn. And in between, I've got everybody out of sync. So the challenge of biochar making is, how do I design a device that takes a significant amount of wood, either sequentially in a continuous flow or all at once, to an intermediate step to get it to char, but doesn't expose it to conditions that let it keep going to ash. It is a challenge. This is a manual that's online, really excellent for cooking. A lot of the earlier work on biochar was stove cooking for the developing countries, and that's where this was stolen from. Stolen being a complimentary term in the academic world, where I at least gave them credit, right? I didn't just steal it. What's with terra preta? You know, come on, we hear about all this stuff, the pottery shards and all the bones and all the other stuff. So if we dig down with some real structure, we find out there's actually 2 terra versions. One's called terra preta, black soil, and the other is called terra mulata. And that's a tan-colored soil. And we found out that the terra preta was the stuff in the villages right where the people were living, and these are the ones that have the pottery shards, the animal bones, the other stuff, and it looks like they were burning their trash. And that's because they would throw everything out the windows and it would accumulate, and they had pottery that wasn't kiln, cured, so it broke easily. These are chamber pots, so they just chucked them all out. And they burned it. Why'd they burn it? Rats. Rats and cockroaches. So that's what they're doing. It's a sanitation move. And that's why we had all this other stuff. When you go outside the village to where they're growing it, we have terra mulata. And it's the stuff that was there for many, many and very broadly spread throughout the landscape. And of course, you've seen this whole thing. Gee, terra preta is this deep soil 5 feet deep, and this is the other soil, and it's worthless stuff. And really what it comes down, I love this. This has got to be the least culturally sensitive picture I've ever seen in my entire life. We're going to the Amazon. We're looking back into their culture. The dirt is 5 feet deep. Hey, white guy, go stand next to it. This will be fun. We can't even find a Native American that did all this work. We're going to take this Norwegian guy and go, he's going like, where do I get my passport stamp? So I got to Brazil. Yeah, I don't understand what they did with this guy. But why is it so deep? Well, I'll tell you. Prior to steel and tools, which we didn't have in the New World, fire was really the only thing you had to shape the landscape around you. And it takes enormous amounts of time to clear land with fire, and once you clear it, you want to keep reusing it. This whole idea of using it, wearing it out, go and do the next one, that doesn't work. So the other aspect is that staple crops that they were growing extract potassium and phosphorus from the soil. And there's no real way of replenishing it in the Amazon except to go and to get the vegetation out of the rivers, which take phosphorus and potassium out of the water and store it in the plants as they grow, and take them up top and burn them next to your fields to release the potassium and phosphorus. So it was in fact a fertilization method. It was not, it had the side benefit because it was wet stuff of depositing this carbon. And it does help the fertility, but I guarantee you, and how do I think I can guarantee you? Well, ignoring the PhD, which means I'm often wrong, but never in doubt, I called up Susanna Hecht out of UCLA, who did a lot of this original work. And she said, no, you just can go down to the Amazon today. They do it today. They bring the aquatic vegetation up and they burn it to release the fertilizer. If they don't get the crops. If you don't get the crops, you don't come back next year to grow more food because you're dead, man. That's how it works. So they had to keep doing this year after year after year. If plants grow in 6 inches of soil. You don't do 5 feet of dirt if the plant's going to use 6 inches of it. It's a lot of work. But you do keep building it up if you got to keep fertilizing every year. So this makes a lot more sense to me. That this is the reason the terra preta occurred, and we see this thing. But it's not tremendously removed from the mere requirements of fertilizing plants for crops year after year. However, that carbon value, that carbon persistence and the residual value is clearly evident because those soils are much more fertile to this day. All right, options for, there's a fair number of slash piles out there. And Chris gave me a great tour this morning, and I tell you, it's not as bad as I feared. Because I really thought that these things were what I can visualize as slash piles, which are logs, they're trees that are dropped, and they're serious. There's a lot of weight there. So the idea as a starting point, and that estimated 11,000 tons is not nearly that, is to convert it to biomass, into biochar to prevent it from degrading, because even though it's pretty stable because it's so dry out there, but it's not going anywhere, and it's not going to do anybody any good out there, except for the critters that live in it, right? We saw like Bambi out there. It was unbelievable. So let's make biochar to prevent degradation, ultimate rotting, and then we'll get a supply of biochar for studies, for sale. We're going to prime that pump to start doing that research. And we didn't get a copy of that had the pictures. So there are devices, I'll just describe them. They are called, the air burner has one called the Char Boss. There's a much larger device made by somebody called Tiger Cat. the Tiger Cat one is really overkill. It does 20 tons an hour, and really it's designed for disposal yards that are going to have just, you know, landscaping debris here, hurricane cleanup, this kind of stuff. But I really think the Char Boss is going to be the thing that you can roll around, chuck the stuff into, and thief off the Biochar. They've modified the standard air burner version. The Boss series has tires on it, so you can pull it behind essentially a heavy-duty pickup truck and move it from place to place. Yeah, you're going to need a front loader or a backhoe with a thumb on it, a hook, to feed it. And then you're going to be able to get some char out of it. And there's a fair amount of expertise. You got to learn how to do it, but you'll get good at it. And we're not really, because the biomass is already there and it's not going to have to get bought, we're not really, you know, wrestling with getting 25% yield versus 20% yield. We're just interested in moving out some biomass and getting some char to work with. We're going to have plenty of char when we get this process going. So I'll flesh that out. I apologize. This was a glitch that I discovered en route. And this is Ghost of Christmas Future. This is where people are advocating that the pyrolysis plant, now you've got this massive stream of biomass waste coming in, but it can create a material which is essentially a platform material. It is a soil amendment that holds water, it's got activated carbon properties, it's got cation exchange, it's got all the soil attributes we want. Why? Because soil co-evolved with it there. So all these microbes and all these plants learned how to take advantage of biochar's presence in soil. You know, we're just reintroducing that. But then you've got concrete, which is a complete energy pig to make. A lot of emissions, just the whole concept of just offsetting certain emissions from steel and certain other properties, feeding it to cows. Europe feeds about 90% of their biochar production to animals. First step. Coming out of the cow, we then take the manures that have the biochar in them and we start cascading them down into the agricultural applications. So I tell people in a simple sense, there are four ways to make money in biochar. One, get paid to take in your raw materials. Two, get paid for the heat it throws off that you could use. Three, use it as you make it as an absorbent to detoxify things. Clean up water supplies, get rid of land, marginal lands, etc. And four, cascade it ultimately into the soil to be the long-term improvement of that soil. And those are the four opportunities, and we can work on making them work, but we're seeing an explosion, not the least of which is associated with the fact that every one of these non-re-emitting applications keeps CO2 here, and we got to start doing that. And you're thinking, I'll think for you, holy macro, that man is like listening to a Gatling gun. Now, there are cultures where that's just a huge compliment. We're not one of them. But let's answer some questions, kick around some ideas if it happens, and then we're going to take a break. We need a break, stretch out, change the blood in our legs. And then we're going to talk about where does biochar fit in our future, our being the human race. And two, how might it fit in Texas State's future, a little bit more focused. But let's do questions. If someone knows how to make lights come up, yes, sir.